Good morning, respected sir. And my name is Charanya. I am from AML E section department and my roll number is 38. Today I am presenting about evaluating the line integral for electromagnetic field intensity in motor coils. Evaluating line integrals for electromagnetic field intensity in motor coils. Introduction to line integral in electromagnetism. Line integrals are fundamental tools for analyzing electromagnetic field along a path. They measure the cumulative effect of fields as it varies along a specific trajectory. Understanding their application in motor coils is essential for optimizing motor designs and performances. This is the relevant image for introduction to the line integral in electromagnetism. How to understand calcular integrations, definitions. In physics, all formulas shown to the concepts as functions of either time or position. Next, electromagnetic field intensity in motor coils. The electromagnetic field intensity describes the strength and direction of the magnetic field within the coil. It is influenced by the current, coil geometric and magnetic permeability of materials. Accurate evaluation of intensity is crucial for predicting motor efficiency and torque. This is the relevant image for electromagnetic field intensity in motor coils. The electromagnetic field intensity describes the strength and direction of the magnetic field within the coil. It is influenced by the current, coil geometric and magnetic permeability of materials. Accurate evaluation of this intensity is crucial for predicting motor efficiency and torque. This is the relevant image for electromagnetic field intensity in the motor coil. Fundamental concepts of line integrals. A line integral sums the field vectors components along a specific path. Mathematical, it is expressed integration C. I can't read. It provides a scalar or vector quantity depends on the nature of the field and the integrals. Evaluating line integrals show that differential forms in integrations are exact. They evolve the integrals. Integration of 0, 0, 0 of 2, 3, minus 3 2x dx plus 2y dx plus 2z dz. Next, the role of line integral in magnetic field calculations. In magnetostatic, line integral helps determine magnetic flux and induces EMF. They are used to evaluation the magnetic potential difference along a coil. Such calculations are fertile for understanding energy transfer in motor operations. They are used to evaluate the magnetic potential difference along a coil. Such calculations are vital for understanding energy transfer in motor operations. This is the relevant image for the role of line integral in magnetic field calculation. Electromagnetic field due to the flow of the current. This is the relevant image. Mathematical formula for motor coil. The magnetic field. The magnetic field integration math wave around a coil can be integrated along a path to find flux. The line integral qualifies quantifies the magnetic flux linkage. Proper choice of path align with the coil geometry for accurate results. This is the relevant image for the mathematical formalization for motor coil. Determining the path for integrations. The paths should follow physical content of the motor coil. For a solenoid, the typing. For the solenoid, the path typically runs along the coil interior and exterior. In complex numerical methods are often employed for integrations. This is the relevant image for determining path for integrations. Superconducting electromagnetic coil. Simplifying assumptions in calculations. Symmetry and uniform current distribution assumptions simplify the integrational process. These assumptions helps derive analytic expressions for magnetic fields. There are valid under idealization conditions, but require validation in real world applications. This is the relevant image for simplifying assumptions in calculations. Analytic techniques for line integral evaluation. Direct integrations involves substituting the magnetic field expressions into the integral. Techniques such as Boyce-Savart law are used to compute closed form solutions. Are possible for simple coil geometries, but complex cases often need numerical methods. Electromagnetic coil. This is the relevant for analytic techniques for line integral evaluation. Electromagnetic coil. Numerical method for numerical methods for complex geometry. Finite element analysis in commonly used to evaluate magnetic field in intricate coil designs. Disguising the path into small segments or allows for approximate numerical integrations. These methods produce high accuracy but requires computation resources. The relevant image of numerical method for complex geometry, electric electromagnetic field due to the flow of current flow of the current is a relevant image. Solenoid coil. Practical application: calculating magnetic flux. Magnetic flux is obtained by integrating over the coil across sectional area. Line integrals helps determine the flux linkage with which influences induce EMF. Accurate flux calculations are essential for motor efficiency and performances. Evaluating electromagnetic field intensity. The field intensity can be derived from the line integral results and magnetic flux calculations. It provides insights into the magnetic environment within and around the coil. This evaluation assigns in optimizing coil design to the maximum performances. This is a relevant image for evaluating magnetic field intensity. Electromagnetic field due to the flow of current. Challenges in line integral evaluation. Complex coil geometries are non-uniform current distribution, complicate calculations. Material properties and magnetic saturation effects may require advanced modeling. Balancing computation efficiency with accuracy is a key challenge in partial applications. Case study evaluation in motor coil. A typical case involves defining the coil geometry and current distribution. Numerical integrations methods are used to compute the magnetic field along the coil path. The result inform design's choice to improve magnetic flux linkage and torque output. This is the relevant image for case study evaluating a motor coil, electromagnetic coil. Summary and key takeaways. Line integrals are essential for analyzing magnetic fields in motor coils. Proper path selections and integration techniques are critical for accurate results. Combining analytic and numerical methods ensures the analysis of complex coil geometries. Conclusion. Here is the image for the reference image for summary and key takeaways. Conclusion and further direction. Advances in computational tools continues to improve the evolution of electromagnetic field. Integrating these methods into motor design accelerates development cycle. Ongoing research aim to refine models for better accuracy in complex electromagnetic environment. This is the relevant image for conclusion and further direction. Evaluating the line